So, if hydrogen is widely used as a future energy carrier, storage will be needed to meet time-varying demands for fuel, as is the case for natural gas and gasoline today. This includes large-scale bulk storage of hydrogen, intermediate-scale buffer storage, and small-scale storage near the point of use. For example, fuel storage on vehicles. Stationary storage technologies used commercially by today's industrial gas suppliers of chemical hydrogen are applicable in a future hydrogen energy system. Onboard hydrogen storage systems for vehicles are being developed. Here we review the status of commercially available hydrogen storage technologies and discuss options now under development. A. Large-scale stationary production of hydrogen. Stationary storage. Very large quantities of gaseous hydrogen could be stored underground at several hundred to 1,000 pounds per square inch in depleted oil or gas fields, aquifers, or salt or rock caverns. Underground hydrogen storage has been done commercially in two cases. ICI stored 95% pure hydrogen in salt caverns at Teesside, England, for use by industry customers, and Gaz de France stored town gas containing 50% hydrogen in an aquifer. Underground formations typically have very large capacities, less than 1 billion normal meter cubed of gas for aquifers or gas fields, and millions of NM3 of gas for caverns. So NM3 is normal cubic meters. For gas wells and aquifers, only a fraction, typically from 1 to 2/3, of this capacitor is accessible per storage cycle because the rest of the volume must be filled with cushion gas to maintain pressure. Rock caverns allow perhaps 25% turnover in capacities per storage cycle, and wet salt caverns may approach 100% turnover. These systems could provide on the order of 1 million to 10 million NM3s of hydrogen per storage cycle, equivalent to the fuel needed each day by a large refinery complex or by a fleet from 0.3 to 3 million hydrogen fuel cell cars. The levelized cost of large-scale underground storage is estimated to add about $2 to $6 a gigajoule to the cost of hydrogen. Higher costs are found if the storage system is cycled seasonally, only once or twice per year rather than daily or monthly. For natural gas, large-scale seasonal underground storage is used in North America today, primarily because of the strong winter peak for gas-fired residential heating. Assuming that hydrogen is used mostly for transportation rather than heating, seasonal fluctuations would not be as large, so little if any seasonal storage capacity would be needed. Rather, storage on a daily to weekly scale would be appropriate, implying lower storage costs. Another option that has been proposed for handling daily fluctuations in demand is pipeline packing, storing hydrogen in gas distribution pipelines. However, for relatively short local pipelines, the storage capacity would be small. For example, a 30-kilometer, 3-inch diameter hydrogen distribution pipeline serving 5 hydrogen vehicle refueling stations could carry a flow of 5 million SCF of hydrogen a day. Assuming that the pipeline operated at 1,000 psi, the storage volume available in the pipe would be 340,000 SCF, or only 7% of the total daily flow rate. So next we have stationary storage at intermediate and small scales. For intermediate to small scale hydrogen storage, liquid hydrogen and compressed hydrogen gas in cylinders are used in the industry today. Liquid hydrogen storage. Hydrogen is liquefied by reducing the temperature to very low levels. Hydrogen becomes liquid at minus 253 C. Liquid hydrogen is stored in cryogenic dewars, vessels designed to minimize heat loss. Hydrogen dewars range in capacity from a few kilograms for laboratory use to a few hundred tons. An advantage of liquid hydrogen over compressed gas is that dewars are more compact than compressed gas cylinders, so that truck delivery is less costly, because more energy can be delivered per truckload with liquid than gas. Liquid hydrogen is favored if modest quantities of hydrogen are to be transported long distance, where pipeline costs for gaseous hydrogen transport would be prohibitive. For these reasons, merchant hydrogen, e.g. hydrogen delivered for industrial purposes, is often liquefied for storage and delivery by truck. About a third of merchant hydrogen delivery is by liquid hydrogen truck, and the remainder by short-distance pipeline or compressed gas truck. A disadvantage of liquid hydrogen is that the capital cost of liquefaction and storage equipment is significant. Moreover, there is a large energy cost. Electricity equivalent to about 1/3 or more of the energy value of hydrogen is needed to liquefy. Liquefaction and storage typically add $5 to $10 a gigajoule to the cost of liquid hydrogen. Depending on the scale of the liquefier, about as much as the cost of gaseous hydrogen production. For a large-scale energy system, the energy conversion losses are higher costs make liquefaction and truck delivery less attractive than gaseous pipeline distribution or on-site production from natural gas. So this suggests that liquefaction is an excessively, prohibitively high cost to do. So gaseous works, which makes sense when we look at Germany's 20% gaseous replacement. Above ground compressed gas storage. For storing relatively small amounts of hydrogen on the order of a few million SCF or less, industrial consumers of hydrogen sometimes use above ground compressed gas storage and pressure tanks. Compressed gas pressure vessels are commercially available at pressures of 1,200 to 8,000 psi, typically holding 6,000 to 9,000 SCF a vessel. Pressure vessels are configured in rows or in stacks of tanks. Tank storage is modular with little economy of scale. Capital costs for pressure vessel storage are $3,000 to $5,000 a gigajoule of storage capacity. Compression from production pressure, typically 1 to 15 atmospheres, to storage pressure adds capital and electricity cost. Hydrogen compressors are commercially available over a wide range of sizes. In a survey of small industrial users, sometimes reading is hard. In a survey of small industrial hydrogen users, Fine and Edwards found that storage and pressure vessels adds 2 to 20 gigajoules depending on the application. Ogden et al. Have estimated that costs for compression and pressure vessel storage of 0.025 million to 0.5 million SCF of hydrogen at a hydrogen refueling station might add $2.5 to $4 a gigajoule to the delivered cost of hydrogen. Another recent study considered that the cost of storing 0.6 days production at a central hydrogen plant, producing 23 million to 234 million SCF a day, finds an additional cost of $2 to $4 a gigajoule. Oof. Storing hydrogen on board vehicles. Unlike gasoline or alcohol fuels, which are easily handled liquids at ambient conditions, hydrogen's a lightweight gas and has the lowest volumetric energy density of any fuel at normal temperature and pressure. A viable onboard automotive hydrogen storage system must be compact, lightweight, low-cost, rugged, easily and rapidly refillable, and, of course, safe. See below for a discussion of hydrogen safety. Moreover, it must be capable of storing enough hydrogen to provide a reasonable traveling range and good dormancy, i.e. the ability to retain hydrogen for a long period of time without a leak. A number of alternative methods for onboard hydrogen storage have been considered. These are shown in Table 3, which give the projected volume and weight of alternative hydrogen storage systems containing 3.5 kilograms of hydrogen, enough for a 380-mile traveling range in a mid-sized hydrogen fuel cell automobile. Oh wow, that's really good. 3.5 kilograms of hydrogen is... What does gasoline weigh per gallon? How much does it get? Why can't you just tell me how much a gallon of gasoline weighs? None of this is useful. Okay, gasoline weighs roughly 6 pounds a gallon. So, for the same weight, at about 6 pounds, you have enough for a 380-mile traveling range for a gallon of gasoline. Talk about changing the weight efficiency of your car. So, several methods have been demonstrated for storing hydrogen on experimental vehicles. Each onboard storage method has advantages and drawbacks. Ooh, the pros and cons, so I don't have to. Storing compressed gas in high-pressure cylinders has been used recently in the Ballard and Daimler-Benz fuel cell buses and the Daimler-Benz Neckar 1 and Neckar 2 fuel cell minivans. Ford has explored this option in a recent assessment, as have researchers Lawrence Livermore National Laboratory and Thickle. Interestingly, the university I went to for my bachelor's had a hydrogen car as well. Well, it was more of like a bus. It was like an 8-seater or something like that. I don't remember. I always walked. I didn't use it. Liquid hydrogen storage in a small dewar. Researchers at DFALR and BMV, Messer, Grisham, and Lind have developed technologies for liquid H2 on a vehicles and for refueling. One variant of the Daimler-Benz Neckar 3 uses Neckar 4, uses liquid hydrogen. Metal hydride storage. Metal hydrides are compounds in which hydrogen is absorbed by a metal under pressure and is released when heat is applied. This technology was used by Daimler-Benz and in experimental hydrogen vehicles in the 70s and 80s, and by Toyota in 1997 hydrogen fuel cell demonstration vehicle. Compressed gas is simple to implement. Refilling is as rapid as that for gasoline, a few minutes or less. Dormancy is good, and the energy requirements for compression are modest. Electrical requirements for compression to high pressure are typically 5 to 7% of the energy content of the hydrogen and can be lowered if hydrogen is produced at a high pressure. Although the energy density per unit weight and volume is low with conventional steel pressure cylinders, advanced composite high-pressure cylinders hold the promise of acceptable weight, more than 10% hydrogen by weight, and large but probably acceptable volume. Conceptual designs have been developed by Ford Motor Co. for lightweight, potentially low cost, at $500 to $1,000 a tank in mass production. High pressure, greater 5,000 psi hydrogen tanks holding more than 10% hydrogen by weight, which can be refilled in 3 minutes. Recently, Middlesky et al. Have estimated that a tank carrying 3.9 kilograms, enough hydrogen to power a mid-sized fuel car about 380 miles, would weigh less than 40 kilograms, and would take up perhaps 190 liters of space. Tests of these lightweight pressure cylinders would be conducted by researchers at Lawrence Livermore National Laboratory in Thiokol later this year. By contrast, current onboard metal hydride systems store only 1 to 1.5% of hydrogen by weight, are costly, and require a relatively long recharge time of 10 to 20 minutes. Heat must be applied on the vehicle to release hydrogen, which involves the use of an onboard burner and heat exchanger. An advantage is the relative compactness of metal hydrides and their relatively low charging pressure, several hundred psi, as compared with compressed gas cylinders of several thousand psi. Liquid hydrogen is attractive in that it offers a low weight and volume per unit of energy. This has led some researchers to prefer liquid hydrogen as the most capable of providing long range. With liquid hydrogen, boil off of cryogenic liquid from storage, poor dormancy, and refueling losses have been issues. Onboard storage and refueling systems for liquid hydrogen-powered vehicles have undergone significant improvements in recent years, so that these problems are much less severe. For example, less than 1% boil-off would be expected per day from a current liquid hydrogen tank, and refueling could be accomplished in a few minutes. Still, the total fuel cycle energy efficiencies is significantly lower for liquid hydrogen than for gaseous hydrogen, because of the large amount of energy required for liquefaction. If greenhouse gas emission reduction and efficient use of primary resources are motivators for adopting hydrogen, then liquid hydrogen routes are less attractive than are those for gaseous hydrogen. Moreover, liquid hydrogen is likely to give a higher delivered fuel cost than compressed hydrogen gas at large-scale energy systems, because of the high cost of liquefaction. Recently, researchers at Lawrence Livermore National Laboratories have proposed using a hybrid compressed gas liquid hydrogen storage system made up of insulated high-pressure cylinders that would allow operation on compressed gas for short trips and operation on liquid hydrogen when a long range was needed. Such systems are undergoing preliminary tests and would reduce the energy used as comparable with a pure liquid hydrogen system. Considering both storage and refueling technologies, the most promising near-term alternative is probably compressed gas storage. it appears that hydrogen can be stored in advanced compressed gas cylinders at acceptable cost, weight, and volume for vehicle applications. This is true in part because hydrogen can be used so efficiently in fuel cells that relatively little fuel is needed on board to travel a long distance. Development of lightweight, low-cost, high-pressure tanks is a priority. Liquid hydrogen appears to be technically feasible, especially with improved systems, but ultimately cost and energy efficiency considerations favor compressed gas for hydrogen energy systems. Interest. What they did not discuss is, well, I don't know if we'll get there yet, but I don't think we will. There's a little bit of a play we could have discussed here, where you could use gaseous hydrogen and put it instead of natural gas in the pipelines, and then that can be used to refuel your car at home as well. So you can use part of that local storage of natural gas or hydrogen as part of the storage for your fuel tank as well. So you pull up and plug in, and then you can just refill on hydrogen in your garage or on the street outside your house. But in a similar way you use electricity right now, or if you have a gas cooking top, think of, instead of cooking or water heating, you are just refilling your car, the same system. That'd be interesting to me. Probably more cost effective based on what we've read so far than having a bunch of small scale hydrogen generators on your neighborhood or in your house is to have a slightly larger neighborhood one that just pumps hydrogen into your neighborhood. I think that's an interesting thing to think about. So D, novel approaches to hydrogen storage. Apologies. A variety of innovative storage methods for hydrogen are being researched. Storage of hydrogen in carbon materials. So carbon is an attractive medium for hydrogen storage because it is readily available and potentially low cost. A number of approaches based on hydrogen storage and various types of carbon are being pursued. A team of scientists at Northeastern University is investigating hydrogen absorption in graphite nanofibers, recently reporting storage of greater than 50% hydrogen by weight. If this result is verified, it could have strong implications for future hydrogen storage systems. Work is also ongoing on hydrogen storage in carbon nanotubes. Others have proposed storing hydrogen in fullerenes or in activated carbon at low temperatures. Development of improved metal hydrides and alternative hydrides. One goal is to develop metal hydrides that store more than a few weight % of hydrogen, which are potentially low cost and are readily charged and discharged. For a review of metal hydride technology, the reader is referred to these three. Polyhydride materials are an alternative approach, and liquid organic hydrides have been considered as a method for bulk hydrogen storage and transport. High pressure in glass microspheres. Various researchers have proposed high pressure storage of gaseous hydrogen in glass microspheres, which can be transported in bulk without the need for an external pressure vessel. Others have proposed hydrogen storage in zeolites or as a cryogenic slush for use in advanced planes and rockets. Although these approaches offer potential improvements in energy storage density or cost, all are still far from commercialization. So, summary of storage options. Existing commercially available stationary storage options could be used in a future hydrogen energy system. Development of practical, high-pressure, lightweight, low-cost, onboard, compressed hydrogen storage for automotive applications remains a high priority. A range of research and development projects on advanced hydrogen storage concepts are being pursued. Improving hydrogen storage systems has been proven to be a difficult challenge. If a breakthrough hydrogen storage technology were successfully developed, it might speed the introduction of hydrogen as a fuel.